dear students. Today's topic is molecular orbital theory in continuation with the chemical bonding. So we are going to see molecular orbital theory. It's a fundamental concept in chemistry, okay, explaining how molecules form and behave based on the quantum mechanical behavior of electrons. So you know about the quantum mechanical behavior of electrons. All laws also you know, Hund's rule, upper principle, and Pauli's exclusion principle, everything you know. So based on that, we are going to see this. Okay. It describes molecular structure and bonding by analyzing the interaction of atomic orbitals to form molecular orbitals. That is the idea. So it was developed by Hund and Mulliken, okay, in 1932. So this year and all you can keep in your mind. This is very important. Okay, it offers insights into how molecules are formed and how they stick together. Okay, there are so many postulates given, so you have to read these postulates. Okay, it was created to better understand how molecules form. Okay, how molecules form, it bond and behave, especially for complex cases. That simpler theories we saw, right? Valence bond theory. So that couldn't explain for complex cases. So this molecular orbital theory, it helps us to understand tricky structures like molecules with resonance and multiple equal bonds, giving a clearer view of how molecules behave and their properties. Okay. So valence bond theory and other previous theory face challenges in explaining certain features of our atomic orbitals. Okay. Such as, so what are all the challenges it face? We have to understand. First, all of you take down this. What are all the challenges the other theories, okay, face difficulties in explaining the bonds, okay, for the complex molecule. For example, you can take VBT theory and other basic theory, okay. The challenges in explaining, okay, certain features of atomic orbitals we are talking about, okay. So that means it is a drawback, we can say. What is the first drawback? We can take equivalent bonds. All of you take down this equivalent bonds. In the column of equivalent bonds, you can write a difficulty in analyzing the molecules with multiple identical bonds. Okay. First, equivalent bonds means difficulty in analyzing or identifying molecules with multiple identical bonds. Okay. If the molecule is bonded with multiple identical bonds, it is difficult to identify that. Okay. Like those found in certain organic compounds or resonance structures, we can say. Okay. Take down this difficulty in analyzing molecules with multiple identical bonds, like those found in certain organic compounds or resonance structures. Okay, that is equivalent bonds. Next one is complex molecules. We can say this VBT theory failed to explain complex molecules. So what is in the complex molecules? Inadequate explanation. Okay, for intricate molecules, especially those with delocalized electrons or unconventional bonding pattern. Okay. See, for example, the bonding pattern, we can say, how the electrons are delocalized from one place to another place. Everything, it has to explain, right? So this complex molecule has such a case. So this valence bond theory failed to explain that. Okay. So you can take down in a complex molecule, you can take down, inadequate explanation for some molecules, especially those with delocalized electrons or unconventional bonding patterns. Delocalized electrons and unconventional bonding patterns. Okay. Then third one is predictive ability. Third one, predictive ability. Predictive ability. This we can say there is some limitations in anticipating and describing the properties of molecules beyond some simpler structure. Okay, take down this. What is the predictive ability? There is limitation in anticipating and describing the properties of molecules beyond simple structures. Okay. Then next one, electron behavior. That is very important property. Electron behavior. This also it fails to explain. This VBT and basic theory. Okay. It is having some inability to fully describe electron behavior in molecules. Take down this. Inability to fully describe electron behavior in molecules, especially in cases where electrons are spread across multiple atoms. That is very important. Okay? Take down this also. Inability to fully describe electron behavior in molecules, especially in cases where electrons are spread across multiple bonds or multiple atoms. Okay. Then fifth one, molecular geometry. These are all the disadvantages of those VBT theory. So molecular geometry. So this molecular geometry is nothing but we can say this VBT theory struggles in defining precisely and predicting the geometry arrangements of atoms in complex molecules. Okay, you can say like that. Molecular geometry. The VBT theory struggles in defining and predicting the geometric arrangements of atoms precisely in complex molecules. Okay. Next one is energy levels. Next one, sixth one is energy levels. So this is also very important. Some insufficiency is there in VBT theory in providing an accurate depiction of energy levels. Okay. So accurate depiction is there. Depiction means you can say it is not sufficient. Okay? And electron distributions in larger or more complex molecular systems. This is also, there is insufficiency to spread the molecule. That's what. To spread the electrons in a various energy levels. That is their insufficiency. Okay. You can write in terms insufficiency in providing an accurate depiction of the energy levels, an accurate depiction of energy levels and electron distribution in larger molecular system, in a larger molecular system. Okay. So now we are going to see the theory, molecular orbital theory, its features and everything. Okay. So learn along with me all these features and everything. These are all given in your book. Near about 7 points are given. So this is very important point. Here it says the electrons in a molecule are present in the various molecular orbitals as the electrons of atoms are present in the various atomic orbitals. That's all. Okay. So how the atomic orbitals consisting of electrons of atoms, here also the molecular level you can see. Okay. In a molecular orbitals. That's it. So electrons within a molecule occupy molecular orbitals. Similar to atomic orbitals host electrons in individual atoms like that. The atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals, right? So what it says, similar energies, atomic orbitals of similar energies and appropriate symmetries combine to create molecular orbitals. Of course, without atomic orbitals, there is no molecular orbitals. So atomic orbitals of similar energies and appropriate symmetries combine to create molecular orbitals. Okay. Okay. So while an electron in an atomic orbital is influenced by one nucleus, okay, one electron in an atomic orbital is influenced by one nucleus, while in a molecular orbital, it is influenced by two or more nuclei, depending upon the number of atoms in the molecule. Because in an atom, only one nucleus is there. Here, since it is combined with molecule is combined with two or more atoms, so multiple nuclei is there. Okay, so this makes an atomic orbital monocentric and a molecular orbital polycentric. Like that, we can say. Got it? It is monocentric. It is polycentric. Okay, so this point is very important and easy to understand also for you. Okay. Next point is the number of molecular orbital formed is equal to the number of combining or atomic orbitals. Okay, what is the number of molecular orbital? Combination of atomic orbitals. That's it. So, okay. So when two atomic orbitals combine, two molecular orbitals are formed. One is known as bonding molecular orbital, while the other is anti-bonding. Okay. So the number of molecular orbitals formed, how it is? It is equal to the number of combining atomic orbitals. When two atomic orbitals combine, one should be, they create two molecular orbitals, one bonding and another anti-bonding. Okay. So the bonding molecular orbital with low energy, get my point? The bonding molecular to a molecular orbital we saw from the atomic orbitals only it is. When two atomic orbitals combine, it forms two molecular orbital. One is bonding, another one is antibonding. Okay. The bonding molecular orbital with low energy, that means in the first excited level, we can say in the first state of the molecular orbital, we can say, okay, lower energy is more stable compared to the antibonding molecular orbital. Get my point? So the bonding orbital energy, sorry, bonding molecular orbital has lower energy and hence greater stability. It says than the corresponding antibonding molecular orbital. Just as the electron probability distribution around a nucleus in an atom is given by an atomic orbital, the electron probability distribution around a group of nuclei in a molecule is given by a molecular orbital. You know that what is an orbital? Orbital is nothing but it is the probability of finding an electron in each and every orbital. So that is, orbital is where the electrons are. So the probability of finding an electron. So that is an orbital. So we can able to say electron distribution around the nucleus where it is. So that is the orbital. Like that, nucleus also, I mean, in around the electron distribution around different nucleus, various nuclei or group of nuclei in a molecule is called the molecular, that is the molecular orbital. Okay. So definitely I told you earlier, it always follows Aufbau principle, Hund's rule, and Pauli's exclusion principle. Everything you know. What is an Aufbau principle? The electrons are filled in a, after understanding the quantum mechanical behavior of an atom, Aufbau principle, it explains the electrons are filled in the increasing order of energy levels, right? Then Pauli's exclusion principle, it states that no two electrons can have the same identical quantum numbers. That means if the electrons, you know, in one orbital, for example, in 2s2, we can say two electrons can be accommodated in each and every orbital. You are taking one first electron. First electron lies in the second orbit, S level. Sorry, second orbit, S level. Okay, and then its spin is plus off. So N is same for two electrons. This is first electron, second electron. N is 2 for the first electron, second electron. Both lies in the second orbit. L also same. L is equal to 0 for S level. That is also same. If L is equal to 0, M depends upon. M is the magnetic quantum number. That is the orientation of orbitals. So M is equal to 0. That also here. But what about the spin? Spin is plus off for first electron. Here spin is minus off for the second electron. Got it? So this is plus off. Plus of rotation it goes. Another one is minus of rotation. Can you able to understand this? So this is what Pauli exclusion principle state that. So no two electron can have the same identical quantum numbers. It differs only in spin. Okay. This and all you have to understand. What is the Hund's rule? If there are degenerate levels, see for example, Px, Py, and Pz, three degenerate levels are there. So if the number of electrons greater than the number of degenerate levels. In P level, there are three degeneracy. Suppose if there are four number of electrons, then how it occupies? So it occupies first all the orbital, and then the fourth one pairs. So no two electrons can have, so or we can say the number of electrons greater than the number of orbitals. That means the number of degenerate levels. Then pairing occurs. That is what Hund explained. So when the pairing occurs, when the number of electrons, outermost valence electrons is greater than, or we can say in a particular, yeah, that is the valence electrons in a particular degenerate levels, when compared to the number of degenerate levels, if the number of electrons are greater, then pairing occurs. If it is not so, then it will be lone pair. Okay. So this and all you have to understand. Okay. This is very important. First of all, you must know the bonding and anti-bonding, everything. So this I will explain you. According to wave mechanics, the atomic orbitals can be expressed by wave function. Okay. This and all you know, right? Wait, what is a wave function and everything. So I've explained in the second unit itself. It is characterized by psi. Okay, what is this? Psi. Psi has no physical significance, but it is like a function. I've already explained. The function of Ex means it is the total designation. We are designated this f of x as the function of x. It is the letter for defining. So this f of x can be x squared plus 2x plus 3. Like that it will be. Like that, the chi of x we can say. It is the wave function. Okay. We can say the wave function, okay, represents the amplitude of the electronic waves. So the psi, it represents the amplitude of the electronic waves. Okay, I mean Schrodinger, a scientist, he only suggested this. He only found this everything. In your higher classes, if you're moving into any physics course, then you may able to understand and learn this more. Okay. Nowadays, now you just make a point. This is a function which explains the amplitude of electron waves. All are in the waveform. Okay. So it cannot be solved for any system containing more than one electron. Okay. If a system is containing more than one electron, it cannot be solved. So molecular orbitals, which are one electron wave function for molecules, are difficult to obtain directly from the solution of Schrodinger's wave equation. To overcome this problem, an approximate, okay, method known as linear combination of atomic orbitals has been adapted. For a single electron, we can say for an atomic orbitals, the Schrodinger wave equation, from this we can get a solution and then we can define. But for a molecular orbital, you know, various electrons are there. If there are one electron, but it is having, it is, I mean, the electrons of electron distribution are surrounded by the group of nuclei. So we can say it is not possible to solve the Schrodinger wave equation. So we switch over to LCAO, that is linear combination of atomic orbitals. So how the method is applied? So we are considering homonuclear diatomic hydrogen molecule. Always hydrogen molecule is taken into an example because since it is the basic model, atomic molecular model. So two atoms of A and B, this is a hydrogen molecule. Hydrogen atom in the ground state has one electron in 1s orbital. The atomic orbital of these atoms may be represented by the wave function psi A and psi B. Okay, like this you have represented. Then mathematically, the formation of molecular orbitals may be described by the linear combination of atomic orbitals that can take place by addition and by subtraction of wave functions of individual atomic orbitals. Like this, we can take. What is that molecular orbital wave function? It is a combination of both that must be added or subtracted. Like that, we can take. The wave function is nothing but the amplitude of the electron wave. Electron, you know, it is spinning and then orbiting around. Okay, it has both the motions spinning, that is, it moves plus of rotation, minus of rotation, plus of minus of, it spins and then it occupies the translatory motion so that it is orbitally moved, right? So that it is vibrating. So we can say it can be represented, the spinning is represented in the form of a wave. That is known as, that is carried out by this Schrodinger's wave equation. You are going to apply now what method? Linear combination of atomic orbitals. We are going to combine the atomic orbitals. This method is adapted in this. You must see this. These two functions are now added up or subtracted. If it is added, two molecular orbitals are formed, I told you, no? So one is bonding, another one is anti-bonding. This asterisk, the sigma asterisk, it represents the anti-bonding. Sigma is bonding. So bonding molecular orbital and anti-bonding molecular orbital, it is explained here now. See? This is increasing energy. Graph shown. Psi A. First, one electron is there. You know, everyone knows hydrogen has one electron, one s. Right? This is one atomic orbital. It is now moving into either, this is another one, right? One is upper, one is moving in up spin, another one is low spin. Okay, upper spin and lower spin. These two are now combined and it may form either in the bonding orbital or in the anti-bonding orbital. As I've told you, the bonding orbital has lower energy and it has stability, more stable. That is the one of the features, okay? So anti-bonding is higher in energy, so that the energy, lower energy. So this is increasing energy. When compared to this chart, it is lower energy. This is higher energy. This is higher energy. Okay. So since it is bonding takes place in the lower energy. Okay. Can you able to understand this? So this is how you are going to represent the molecular orbital. Okay, so here it comes, two electrons. Okay, so formation of bonding and anti-bonding, you have to understand. Like you have this can be I mean replaced, or we can say, yeah, it is equivalent to the light phenomenon interference pattern. It is a light phenomenon interference pattern. You might have seen this particular pattern for any kind of waveform. Okay, if two waves superimposed together, here we are talking about in class 12, you are going to see in optics all the interference pattern, two light waves superimposed together. Here, one electron wave, another electron wave. You know that one electron, if you are talking about, the electron spin, okay, and then it orbits. Similarly, the other electron also spins. If one electron spins in the upward, another electron spins in the lower, okay, upward, downward, like upward, downward. So it forms the constructive uh, amplitude, we can say. Constructive, what is the word term it is used? Interference only it is used. Okay. 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 See, for example, I will explain you. So the electron wave, okay, this is one hydrogen atom. From one hydrogen atom, one electron is moving. So another one, if it moves like this, then it forms a constructive interference. That means one plus of another minus of. So it forms a constructive. That means it has maximum, okay? Maximum electron wave, we can say, combination of atoms, okay? Suppose if the maximum is combined with, okay, the minimum. See, for example, see this one way, this is another way, okay? This is constructive, we can say. This one way, this is another way. This is destructive. Because if plus and minus combine, then what will happen? See, this is plus, this is minus. So both are electron wave, both are same atoms, homogenic atoms, we can say. That means hydrogen is what it says, it is actually homonuclear, we can say. That means same. Okay. So both are having same electron wave. So plus and minus we cancel, right? So plus maximum, minus maximum. So these are all cancelled, and we usually call this as destructive. This is